All right, Math 30-2. Today we're going to look at modeling data using sinusoidal functions. So today we're going to solve problems that can be modeled by a sinusoidal function, where the function, the table of values, or the graph may or may not be given. We'll also, given data points, perform a sinusoidal regression, which we have not done yet, to determine an appropriate sinusoidal function to solve problems. So modeling with sinusoidal functions. Here's an example. A nail is caught in the tread of a rotating tire at point N in the following sketch. As the tire rotates, the path traced out by the nail can be represented by a sinusoidal function. The points A and C are the max and min. A is our max, C is our minimum. Points N, B, and D lie along the midline. Jake and Giles were given the following information and asked to determine the height of the nail after 6.5 seconds. The tire has a diameter of 50 centimeters. The tire rotates at 10 revolutions per minute. After 1.5 seconds, the nails reach its maximum height. And after 4.5 seconds, the nail touches the ground. Jake's method. Jake used the information given to write a scale for each axis. Why would he mark 4.5 at the point C? Well, if he writes 4.5 at the point C, he would do that because we're told that at 4.5 seconds the nail touches the ground. So at 4.5 seconds the nail touches the ground. Write numbers at the scale marks on each axis. So we're also told at 1.5 seconds the nails reach its maximum height, so this should be 1.5. So it looks like we're going by a scale of 1.5 along the bottom. 6, 7.5, 9, 10.5, and 12. So there's our time in seconds along the x-axis. We're also told the tire has a diameter of 50 centimeters. So from the bottom to the top should be 50 centimeters, so I should know that that is 50. And we're told that NBD lie along the midline. So if this height is 0 and the maximum is 50, the midline should be at 25. Alright, so we should be able to write all those numbers in our grid. Now it asks Jake to determine the amplitude, the period, and the midline value. So amplitude. How do we find amplitude? Our formula says we take max minus minimum, 50 minus 0, and divide that by 2. So our maximum is going to, our amplitude, sorry, is going to be 25. To find the period, now we take 2 pi and divide it by b. Well, in this case, we know what the period of this function is. If I look at the graph, we don't have a b value, but from this graph, we know that it starts at n, goes up, that happens again at d, going up. So that distance is 6 seconds. So that's our period. So our period equals 6 seconds. And finally, the midline. Well, we determined it was 25, but if I want to use the formula, it's going to be maximum plus minimum, divide that by 2. So that's 25. Part C, determine the equation for the height of the nail as a function of time. And we're going to say that A is greater than 0, so we know the amplitude is positive 25. Express the parameters as exact values. So we know A is 25, and we know D, the midline, is also 25. So we calculate those. We're not sure about the B value, but we know the period is 6. So 6 equals 2 pi over B, or B equals 2 pi over 6. So we know the B value is going to be 1 pi over 3 when we reduce these. All right. So I have my A, B, and D value. I can write the equation H at T should equal A, the amplitude, 25, times the sine of BT. B is a value of pi over 3. Add the D value, which is a positive 25. Part D then says, how far to the nearest 0.1 centimeter is the nail above the ground after 6.5 seconds? So what is the height after a time of 6.5 seconds? Well, we plug in time into that equation. 25 times the sine of pi over 3 times 6.5, add 25. So let's do that. Let's do that calculated work and figure out what that height is. If I go to my graph, at 6.5 seconds, that'll be about here. We're going to guess that that height should be somewhere greater than 25, probably greater than 30, based on our graph here. All right. Let's see what we get. So go to your calculator and let's type this in. We said 25 times the sine of pi divided by 3. Well, pi divided by 3 times 6.5. And we're going to add 25 to that. And we want to make sure that this is in radian mode. It is. So we're fine. So I can press enter. So we get a height of 37.5 centimeters. Very nice. So that equals 37.5 centimeters. So that kind of matches up to our picture up above. It's definitely higher than 25. We guess it should be higher than 30, and it's actually 37.5. All right. So that's what Jake did. Let's find out what Giles does. All right. His method, he decides that he could use the data points N, A, B, C, and D to perform a sinusoidal regression to determine the equation for the height as a function of time. So let's complete the table. So we're told at time 0 the height's 25. It's at the midline N. Point A is the maximum. That occurs at time 1.5, and that maximum is 50. B's back at the midline. That occurs after 3 seconds, and the midline's at 25. C is the minimum. That occurs at 4.5 seconds, which is a height of 0. And D back in the middle. That occurs at 6 seconds, and that midline's at 25. So we've completed the table. Now perform a sinusoidal regression on this data and write the height of the nail as a function of time in this form. So h at t is going to equal, and we're going to get our parameters a, b, c, and d from our calculator. So let's do that. So we know we should go to stat, edit, and in our lists we're going to put the time and the height. So let's clear some lists here. List 2, clear, enter. List 1, clear that one. In list 1 we're going to put our times: 0, 1.5, 3, 4.5, 6. All right. And in list 2 we're going to put our heights. Oh, sorry, this one should have been 1.5. Man. And our heights should have been, I guess we didn't have a 0. Perfect. So at time 0, our height was 25. 1.5, it was 50. 3 seconds. At 3 seconds, it was 25. 4.5 seconds, it was back to 0. And at 6 seconds, it was back to 25. So we've got our data in list 1 and 2. Now, go to our home screen, stat, over to calculate, and it wants a sinusoidal regression. So we have to go down quite a ways to get to that. And there's our sine regression at C. So sine regression of list 1 and list 2. And I'm going to store this in y1. So I'm going to go variables, y variables as a function in y1. So I'm going to store that to y1 as well. So when I press enter, we'll get our sinusoidal regression. So A is 25, B is 1.04719, C is 0, and D is 25. So it asks us to round to 2 decimal places. So let's do that back into our notes. So H of T equals our A value. From your calculator, you got 25 times the sine of our B value was 1.049, so 1.05 T. There was no C value, and our D value was also 25. Now, how far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds? So still looking at H at 6.5. But now if I use the graph, so to get a proper graph, let's change our window settings to match what we had on the previous page. Our x's went from 0 to 12. 0 to 12 by a scale of 1.5. And our y's went from 0 to 50. And we'll go by a scale of 25, which is the midline. So now we graph it. There's what this graph looks like in our notes. We want to know what happens when the time is 6.5 seconds. So trace and hit a time for x of 6.5. And we get the same height, 37.5. All right. So same height, 37.5 centimeters. All right. Now in this example, the equations determined by Jake and Giles were the same. Because of all the data points Giles used were on the graph of the function, recall that it is not often the case that a regression equation is a perfect fit for the data. In most practical examples involving regression, we determine an equation that is the best fit for the given data. So our example, it fit exactly, which is fairly rare. Let's look at class example 1. The depth d meters of water in a harbor t hours after midnight can be approximated by the sinusoidal function given, where t is greater than or equal to 0 but less than or equal to 24. So we're saying time is 1 day. State the amplitude of the equation of the midline and hence determine the maximum depths of water in the harbor. All right, so given this equation, we should be able to do that. So step 1, state the amplitude. Amplitude is the A value. The A value is 5. We want the equation for the midline. So we can find the midline using the formula. Well, the equation of the midline is going to be the D value, so y equals 12. So I can now determine the max and the min. So my midline's at 12 and my amplitude is 5. So the maximum is 17. My midline is 12 and my amplitude is 5, so my minimum is 7. Determine the period of the function to the nearest tenth of an hour. So period is 2 pi divided by b. And our b value is 0.524. So our period should be about 11.99, or we could just say 12 hours. Write a suitable window that can be used to display the graph of this function. Well, we're told time goes from 0 to 24, so that'd be a good x setting. So minimum 0, maximum 24. We can go by 1 hour for time. It makes sense. Y, well, we know the max is 17 and the minimum is 7. So let's say our Y setting goes from maybe 0 to 20. And we can go by a scale of 2, 4, whatever we want. Maybe we'll say 5. D, use the depth of use the graph of the function to determine to the nearest tenth of a meter the depth of water at 2 p.m. So if we go to the question, T hours after midnight, 2 p.m. is 12 plus 2 or 14 hours after midnight. So our T value is 14. So we're finding the depth when the time is 14. So we could plug 14 in for T in the equation, or we could graph that function and see what we get. I would like you to try that and see if you get the same answer I do. So pause it and see what you come up with. So if you're in your graphing calculator, you type the equation into your calculator, 12 plus 5 sine 0.524t plus 1.571. Make sure you have your window setting like we said. 0 to 24 by scale of 1, 0 to 20 by scale of 5 for our y's. You press graph and we see our function for this tide. Hours since midnight, we want time is 14, so hit trace. And at 2 p.m., which is 14 hours after midnight, we come up with a height of 14.474753 and so on. So once it's to the nearest meter, so that depth should be 14.5 meters. Part E, a ship that requires a minimum of 8.5 meters of water is in harbor at midnight. By what time to the nearest 10 minutes must it leave to prevent grounding? Alright, so what we're going to do with this case now, let's graph y2 equals 8.5 meters, and we're going to see where it's going to intersect with our curve. Alright, at what point it intersects with the curve, and then we'll figure out what that corresponding time should be when he has to leave. So we'll go to our graphing calculator, go into y2, 8.5 meters, and graph it. So he's in harbor right now, and if he leaves when it's less than 8.5 meters, he's in trouble, so we have to figure out this point of intersection. So second, calculate point of intersection. First curve, second curve. We want to make a guess closest to that point of intersection. So let's move our cursor over there. Because if we don't tell it to get near that point of intersection, it could pick any one of these four that we see. Alright, so we're now close to that point of intersection. Press enter, and we come up with x is 4.477 and so on. So the point of intersection occurs at x equals 4.477 and so on. So we want to figure out how many hours 0.477 is. So that's 4 hours, and if you take 0.477, you multiply it by 60, you come up with about 28.6 minutes. So 4 hours, 29 minutes. So the question asks, to the nearest 10 minutes, when must this thing leave port? So 4 hours after midnight is 4 in the morning. If it leaves at 4:30, the tide's going to be less than 8.5, so he's probably going to have to leave at 4:20 a.m. If he left at 4:30, it's going to be lower than 8.5 meters, so he would get shipwrecked. He can't make it through there. Part F, what is the next time to the nearest 10 minutes that the ship can safely return to the harbor? Alright, so let's go back to our graph. It can safely return when it gets back to this time. Alright, so let's find that point of intersection. Calculate the point of intersection. First curve, second curve, and now I want to go over here to to that point of intersection. And that one occurs at 7.5129. So now x equals 7.5129 and so on. So 0.5129 is how many minutes? Multiply 0.5129 by 60 and you get 30.77, so maybe 31 minutes. So the nearest 10 minutes, again at 7:30 a.m. it's not going to be high enough, so we're going to have to go all the way to 7:40 a.m. before the water is high enough for the ship to return. All right, great. So you can continue on trying the questions that were assigned. Away you go.